is going to cover the fundamental theorem of calculus part 2. So the fundamental theorem of calculus part 2 is going to be something, again, that we use a lot. We're actually going to use this one more than part 1. So this is what we're going to use to evaluate integrals without having to do that whole big long integration process. Limit process that we did on Tuesday. So what the fundamental theorem of calculus part 2 says, so we're going to say let f be continuous on the interval a to b, the closed interval a to b. So if we take the integral from a to b of f prime of x dx, so if we have the derivative function and we take the integral from a to b, that is equal to f of b minus f of a. Okay, so that's saying the function that you're taking the integral of is a derivative, and it just equals the change of the original function from a to b. Oftentimes you'll see it written like this, a to b, they'll put f of x in the integral, and then they'll use a capital F function for the f of b minus f of a. So in this case, if you took the derivative of the capital F function, it would just be f of x. So f of x in this case is still your derivative. I think it's a bit easier to think about it this way, the first way. And this makes sense to us for things that we've seen before already. Like for instance, if we integrate from a to b, if we integrate a velocity function, the area underneath the velocity graph is really just your change in position over that interval. So that's your change in position over that interval. So we are going to get used to using this a lot. So if it looks very foreign to you right now, don't worry. So what we're going to be doing today is we're just going to be putting this part of this theorem to use conceptually. So we're going to be writing out a lot of equations involving that statement. Okay, so for instance, here we have f is a function defined on the closed interval, -4 to 4, and we know that f of 0 is -3. Okay, so they gave us 1 point on the function. The graph of f prime, the derivative of f, consists of one semicircle and one line segment as shown in the figure below. And we want to find the following values. Okay, so we're given the graph of f prime. We're not given the graph of f, we're given the graph of f prime. So we're given the derivative, and we want to go backwards and be able to find what is f of 4. Okay, so usually if we're given a derivative graph, you can't use that graph to find values of the original function. You can only use that graph to find values of the slope of the function. But if we have the graph of the derivative, and if we have this, our special point up here, if we're given one other point on the original function, we can find another point. So what we're going to do is we're going to use the fundamental theorem of calculus part 2, and we're going to set up an equation that we can then solve for f of -4. What we're going to do is we're going to set up an integral from -4 to 0. We want to start with the lower number first as our left bound of f prime of x dx. Okay. And the fundamental theorem of calculus that we just went over says that this integral is equal to f of 0 minus f of -4. Okay. So the thing is, using geometry, we can figure out what this left-hand side is. And then we've been given what f of 0 is. So then we just can use this equation now to solve for f of -4. So I'm going to go over here, and I'm going to figure out what is, not from 0, what is the integral from -4 to 0 of f prime of x dx. So that is, what is the area underneath the graph of f prime of x from -4 to 0? So be very careful because that is actually this area right here. So if you want to take a moment to pause the video and think about how would we find that area, you can. So what it's going to be is that area in pink is going to be the area of the whole rectangle, which would be, the area of the whole rectangle would be 4 times 2, so it would be 8, minus the area of that semicircle. So that semicircle, the whole circle would be pi r squared, which would be, the radius is 2, so it would be pi times 4, but it's just half of a circle. So it's just half of that, so it would be that divided by 2, so it would be 2 pi. So it's 8 minus 2 pi. So that's what this whole left-hand side equals. I know that f of 0 is -3, and then I have minus f of -4. Okay, so I'm going to add 3 to this side. So I have negative f of -4. If I divide by a negative, then I'll get my f of -4. That'll just switch the signs on the other side. And there we have it. So we're going to do the same process for f of 3. If you would like to pause the video and try it on your own and check, you may. So we're going to set up an integral. One of our bounds has to be 0 because 0 is what we know. I mean, now we know what f of -4 is, but 0 is going to be easier to use here. So 0 to 3 of f prime of x dx, and I know that's going to equal f of 3 minus f of 0. The upper bound always comes first. It's always f of b minus f of a. So let's figure out what is the value of this integral from 0 to 3. So that's this area right here. So the area of the upper triangle is going to be 1/2 base times height. Base times height is 2 times 2. 1/2 that is going to be 2. And then the smaller triangle is has an area of 1/2, and it's negative. And I know that f of 0 is -3, so subtracting that would actually get me +3 here. So I'm going to solve this equation now. It's going to be 3/2 minus 3. So 3/2 minus 3, so it'll be minus 6/2. It'll be minus 3/2. Okay. Our last one here for this page. So we're going to let f be the function defined on a closed interval, -6 to 6. And we again know 1 point on that function. Again, we're given the graph of f prime, the derivative of f. Okay, so what we want to do here is we want to find the absolute maximum value over the closed interval. So when you hear absolute maximum over a closed interval, you should think we need to do the candidates test. Candidates test, which means we're going to test the endpoints and we're going to test any critical points. So let's first find what are the critical points. That's where f prime of x is going to equal 0. So we can find those on the graph. So I'm going to find everywhere where it's 0. I'm marking those right now. That's x equals -4, -2, 2, and 5. So are all of those places where I'm going to have a potential maximum? Let's think real quick. If I had a sine chart for f prime. And I'm going to place my critical values here. If I had a sign chart, before -4 it's negative, in between -4 and -2 it's positive, then it's negative, then positive, then negative. So some of these critical points, I can just tell by the first derivative test that they would be minimums. And I'm not looking for any minimums, so I can go ahead and throw them out. So -4 would be a potential minimum, and then 2 would be a potential minimum. So I only want to test -2 and 5. Okay, so I'm going to make a table of values. We need to test our endpoints, and then we'll test our candidates for the maximums. So what I need to do now is I need to figure out what is f of -6. What is f of -6? So I have not been given the graph of f, so I cannot read f of -6 off that graph. So what we're going to do is we're going to do what we did before. We're going to use our integral. Our integral and then our special value here, f of 0. So I'm going to do an integral from -6 to 0. Again, always starting, the lower bound should be your lowest value. Okay, if I take the integral of my derivative, this is going to equal f of 0 minus f of -6. Okay, so take a moment to figure out what that integral would equal. So we need to find the area from -6 to 0. So pause the video and take a moment to figure that out. First triangle has an area of 2, so it would be -2. Second triangle has an area of 1. And then that quarter circle has an area of pi, so it would be minus pi. F of 0 is 3. Okay, so now I can solve for f of -6. This will give me -1 minus pi equals 3 minus f of -6. What I'm going to do is I'm going to actually add f of -6 over and subtract, and add the 1 and the pi over. So I'm just going to kind of flip-flop everything in my equation here. So I'm going to add 1, so it'll be 4, and I'm going to add pi. So this is 4 plus pi. Okay. So now I need to figure out f of -2, so let's do -2 to 0. Set up our fundamental theorem of calculus equation. Luckily, I already know what the integral on the left-hand side is equal to. I had to figure that out for the other integral. So this is going to be -pi. F of 0 is 3. And then I'll find out what f of -2 is. I'm going to flip-flop the pi and the f of -2. Be 3 plus pi. All right, last one. I need to figure out what f of 5 is. So I'm going to make an integral from 0 to 5. And that will equal f of 5 minus f of 0. So we can figure out what the area under the graph, under the curve of f is. Oops, that's f prime, sorry. From 0 to 5. Because of symmetry, I know that the semicircle is going to be -pi. And that triangle is going to be 3. F of 0 is 3. Okay. So this will end up being -pi plus 6. Okay. So let's think about this real quick. After I'm at 5 for f prime, so right here, when I'm at 5, after that, right here, I'm just going down. The derivative is decreasing after 5. So if you think about it, 6 is not actually going to be a maximum. It's going to be less than whatever f of 5 is because the function is decreasing after 5. So I can just go ahead and scrap this one. F of 6 is not going to be my maximum. So you can take a moment to put these values into your calculator, the 4 plus pi, 3 plus pi, and negative pi plus 6. 4 plus pi is about 7.14. 3 plus pi is about 6.14. And negative pi plus 6 is about 2.86. So the maximum value is going to be the 7.14. Whew. That was a lot, but we did it. All right, there'll be one more part that will cover the back page.